Hey everyone, and welcome back to this series on multivariable calculus, and today we're going to be continuing our exploration of integration in higher dimensional spaces. So up to this point we've discussed a few ways of doing integration in higher dimensional spaces, in particular with substitutions, change of coordinates like polar, or even more advanced transformation of coordinate systems using Jacobians and so on. So if we take this double integral as an example, the integral of e to the minus x squared plus y squared with respect to both x and y over some domain D, usually a polar coordinate transformation where x squared plus y squared is equal to r squared and dx dy is equal to r dr d theta is usually a good place to go, especially if the domain is all of R2. But of course, we can easily change this integral very, very slightly. For example, instead of x squared plus y squared, we can make it x squared plus y cubed, and polar coordinate no longer is as trivial substitution. And if the domain D is something more complex, for example, let's assume that our domain is some region that looks like this. Like, how would you even begin to integrate over that particular region where D, in this case, is a subset of R2? Right? So that's pretty much what we're going to dive into today and see how we can at least approximate these integrals when we don't necessarily have analytical ways to explore them. So to start things off in an easy way, let's assume that the domain D is going to be a rectangular domain. And when I say rectangular domain, I don't necessarily mean rectangular in the R1 or the R2 sense. So when I say rectangular, that could mean, a cubic or rectangular prism in 3D or a hyper rectangular prism in higher dimensional spaces. But I'm going to be doing most of the pictures from the perspective of our domain being a subset of R2. So let's assume that our domain is a rectangular domain that ranges from, on the x-axis, let's say xa, all the way up to xb, and then on our y-axis, ya to yb, where y and yb are unequal to each other, and xa and xb are unequal to each other as well. So what we want to do is integrate over this particular rectangular domain. Right? So for example, we could say, okay, what is the integral from minus 5 to 2, the integral from 3 to 7 of sine of x squared plus y squared dx and dy, where we're going to be taking the convention that 3 to 7 is our x integral and minus 5 to 2 is our y integral, right? So what is this integral equal to? So our goal is to integrate over this rectangular domain, but we don't necessarily know how to do it. For example, polar coordinate might be a good place to start for this, but from there, things could get really, really complicated. So how can we approximate this domain? So the first step that we're going to do, and we're going to approach this just like we did with single variable Riemann integrals. For example, we have left endpoint, right endpoint, and midpoint, and trapezoidal, and Simpson's approximation. So we're going to go about it like that. So the first thing that we're going to do is partition our domain, in this case D, and obviously uniformly is going to be an easy approach, but it's not going to be a necessity for us. So for example, our x is going to have different spacings, and we can divide this by xb minus xa all divided by m, and we can say that delta y is going to be yb minus ya all over n. This is going to give us m times n smaller rectangles. All right, so in our particular picture, let's assume that m is equal to 4. So we're going to be doing 1, 2, 3, and 4. So that's going to give us 4 regions. And then let's assume that n is equal to 3. So 1, 2, and 3 regions here. So what's that going to give us? Well, that's going to give us 4 times 3, or 12 smaller rectangles, right? So this is going to be our partition of our domain, and notice that everything is going to be accounted for in terms of a smaller rectangle. Once we have our domain partition, then what are we going to do? So step 2 is to tag this partition. So tag your partition with some point on the interior, it's usually the goto, or the boundary, where each subpartition ideally does not share common points. All right, so if we look at one of our smaller rectangles, what are we going to see? So let's take a look. So if we draw one of our rectangles as follows, let's assume this is one of them, we can technically pick any point inside of this rectangle. But what I mean by you don't share common points, for example, let's assume for this rectangle we choose this northeast point, right? Keep in mind there's most of the time is going to be another adjacent rectangle over here. Do not choose the southwest corner of that box, because that's going to be the same thing as the northeast corner of this box. So that's what I mean by do not choose the same exact point, ideally, for adjacent subpartitions. Right? So we could choose any point on the boundary or the interior. So for example, we could choose the northeast, the northwest point. We could choose the southwest point, and we can also choose the southeast point. So those would be the intercardinal points that you could choose. Or you could choose the cardinal points, north. You could choose east. You could choose south. And you can choose west, right? So you could choose the intercardinals or the cardinal boundary points, or you could choose, for example, the midpoint, because you might remember from single variable calculus that the midpoint approximation on average gave us better approximations than, for example, left or right. Or you could choose literally any point that is also inside of this region. For example, I could choose this point right here. That can be our point of choice, or it could be just some completely random point inside this grid. Now let's assume that this point is, say, xi, and then let's call it yj. So xi, yj, and let's call this point pk, where k ranges from 1, 2, all the way down to m times m. Right? So in terms of indices, obviously I is going to range from 1, 2, down to m. J is going to range from 1, 2, down to n. K is going to range from 1, 2, down to mm. So in terms of notation, let's assume that xi, yj, is defined in terms of notation in some sense as a vector. Let's call it x hat k, so that's going to be representing some vector. And then let's assume that m times n is defined to be some other natural number, say capital M. So how are we going to approximate our double integral over this region D? So the double integral of fxy dx dy will then be approximated by summing up these regions, right? And keep in mind, for double integrals, this is approximating the volume, so we should have a length, a width, and a height. So this is going to be the sum from k is equal to 1 to capital N of f evaluated at each of those points, x hat of k, and then since we're using uniform partitions, we're going to multiply it by delta x and delta y. So delta x is our length, delta y is our height, and xk is, for example, our width. So this gives us our approximation, right? And another thing to note, that for uniform partitioning, both of these are constants, so you technically could factor them out of the sum in order to make your computation a little bit more easier or faster. But most of the time, the domains that we integrate over are not rectangular domains, so let's take another step up in terms of difficulty to see how we can adapt to, for example, variable domains. So we automatically have several different ways to approximate multiple integrals that are bounded on integral domains that are rectangular, but what if we have variable domains? So you might be thinking, well, what exactly do I mean by a variable domain? It's where the domains of integration are usually variables or functions of the variables you're integrating with respect to. For example, we can integrate x from 0 to 3, and then integrate y from 0 to x squared. So this obviously is not a rectangular domain, but more so subset of one, in particular a parabolic domain. And then we have your integrand, for example, sine of x squared plus y squared, and then we have dy dx. All right, so here dy is there and dx is there. Be careful, I have seen some people switch around these differentials and pretty much use some other different convention of the order of integration, what they mean. But regardless, what our domain here, obviously not rectangular. So we have our x-axis here, our y-axis here, and we're going to have two different functions, right? We have y is equal to 0 and y is equal to x squared. So we know that y equals 0 is going to be this horizontal line, and then y equals x squared is going to be this parabola here. And then our bounds are x is equal to 0 to x is equal to 3. So x equals 0 is this line here, and then x equals 3 is this line here. Right, so our domain that we're integrating over is this region. Right, so this is our domain D. Right, so we can write this in a more compressed form as the double integral all over D of sine of x squared plus y squared dx dy, or the derivative with respect to our region. Right. So how can we approximate the integral over this non-rectangular region? Obviously, there's going to be several approaches, but I'm going to give you one approach that you could take here, because there's definitely some amount of creativity that one could do. Right, so step one. So what we can do is we can approximate your domain, in this case D, with a union of rectangular subdomain approximations. Subdomain approximations. And let's call this dr, right? R for rectangle, D for domain. So this is going to be some approximation. So for our example, x, keep in mind, ranges from 0 to 3, and y ranges from 0 to x squared. So what we're going to do is we're going to choose a value of m and then choose a value of n. So for x, we're going to let m be equal to 4, and this is going to be a uniform partition of our domain. And then for here, we're going to let n equals, some number of your choice, for example, 3. And what we're going to do is we're going to do some type of rectangular approximation like we did in single variable calculus. For example, let's do right rectangle approximations. Right rectangle approximations. And if you don't remember how to do left-hand rectangle, right-hand rectangle, and so on approximations from single variable calc, definitely give that a look, because that gives you a few options. So what we're going to do is we're going to approximate our domain. Right? So for x, we're going to partition it into 4 uniform regions. So for example, 1, 2, 3, and 4. And then we're going to do right-hand rectangle approximations for each of them. So for example, if we go here, that's going to give us a right-hand rectangle approximation, our next right-hand rectangle approximation, our next rectangle approximation, and then our right-hand rectangle approximation. Now we're going to completely ignore the blue and focus only on the green, which are rectangular domains, and we know how to partition them. So notice that in this picture, we're going to have delta x here, delta x here, delta x here, and delta x here. And that's only because delta x can be easily approximated to be a uniform, because x is across, in some sense, a sub-rectangular domain. But notice that our y value is stretching as we progress across different values of x. So obviously our delta y is going to change as we progress against our domain. So if we focus on our first rectangle, we're going to approximate it with 3 subrectangles, so 1, 2, and 3. So this little piece right here, that's delta y 1, let's say. And if we look at the next rectangle, we're going to have 1, 2, and 3. So this little piece here, that's going to be your delta y, let's say 2. And then if we go upwards to our next rectangle, for example, 1, 2, and 3. So this distance right here, for example, could be delta y 3. And then we can progress onto the last rectangle, our largest rectangle, so 1, 2, and 3. So this would be, for example, delta y 4, right? So notice that delta y is not staying constant, right? So delta y is subscripted from, say, 1 to 4 in this case, because we have 4 regions with respect to x. Now, you can obviously see the downside with this approach, because as our domain height gets larger and larger, this region right here is obviously going to be an over-approximation compared to the smaller one, where it's obviously going to be a smaller but still over-approximation for our domain. But obviously, as m and n go to infinity, that error obviously should converge to 0. Right? So once we have this, now we're going to tag our domain partition. And keep in mind our domain partition is dr with, obviously, m times n points. For example, if I go over here, if I do midpoint tagging, then I'm going to have that point, that point, that point, this, 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 and that point, and that point, right? So that's going to give us 4 times 3, which is 12 tag points to project for our height. So if we look at how that would go for our calculation, so for example, if we go with midpoints, not the cardinals, not the intercardinals, but the midpoints of each of those regions, then xi would be equal to 4 minus 0 all over 2 times m plus j, where j is equal to 0, 1, 2, and 3. So what we're looking at here, so this is going from 0 to 4. And then we're going to take this point and then project upwards. Right, so this is j is equal to 0, j is equal to 1, j is equal to 2, and j is equal to 3. Work out that formula just to make sure that definitely gives you what you want. And now let's introduce a little bit of notation. Let g of x be equal to x squared. So this is going to be our upper bound for our heights. And then we're going to let yi going to be equal to g of our xi. And that's going to be divided by, and let's use a subscript of j. So obviously that can be independent. And this is going to be plus k gxi all over n. So what we're doing in this particular picture, and here j is going to be equal to 0, 1, and 2 since we're using 3. So in each of these projections, notice we have 0 to x squared, and this is our height. So if we just do gx divided by 2n, that's going to give us our particular midpoint, let's say. And then this other point is going to just allow us to jump up 1, 2, and 3. So for example, when j is equal to 0, that's going to give us this point, because it only looks at the height divided by n, which gives us that upper bound, and then divide by 2 shifts it half of that distance down. And this is going to increment it a full interval. So this is going to bounce up here, and then it's going to bounce up to that point. So that's pretty much the idea in this particular implementation. Right? And notice that j is going to depend on itself and not I. For example, this one is going to be smaller, and then this one is going to be a little bit larger, and then this one is going to be larger, and the last one obviously is going to be the largest one for our particular example. So once we have our points xi and yj coded, then we can say that, okay, well, xi, yj is then going to be coded into some vector, let's say xk, where k is equal to 1, 2, all the way down to mn. And then our double integral, again, is going to be coded approximately. So dx dy will be, again, approximately equal to the sum from k is equal to 1 to capital N. That's going to be the product of those two. And then f of x hat k times delta x, because that's uniform, and then delta y, and then let's subscript that with k, right? So notice that this k depends on both I and j. So for example, if we're doing the first things first, delta y 1, 2, and 3 are going to be the same, and then 4, 5, and 6 are going to be the same, 7, 8, 9 are going to be the same, and 10, 11, 12 are going to be the same. But that gives you one way of approximating that double integral. As you can see, if the domain variables are extremely complicated, this process obviously gets a little bit more convoluted. So let's see if we can get a more adaptive way of approximating integrals that doesn't completely rely on our domain bounds, with the potential trade-off of error, but as long as we can control that error to some degree, we should be fine. So if our domain is extremely complicated, this is obviously going to lead us to more complicated algorithms if we want convergence or guaranteed convergence to some degree, or where the error converges to 0, especially if the domains belong to higher dimensional spaces, for example, R3, R4, or R52, for example. So what is going to be the solution for arbitrary domains and arbitrary order spaces? I'll give you one that is extremely common in computational math, but it lies in the realm of probability theory. So what we're going to do is we're going to pick random points in some bounding box, which is pretty much a fancy way of saying a higher dimensional rectangle. See if the random point belongs to our domain, and if it does, we use it. And if it doesn't, we don't use it. Let's use a basic example from elementary geometry. So if we have a unit circle, for example, D is equal to the set of all points, x comma y, such that x squared plus y squared is less than or equal to 1, where the boundary is the unit circle, right? So this is x squared plus y squared is equal to 1, and our domain is the interior. So what we're going to do is we're going to find a bounding box for this circle, which we should be able to find because we know the minimum and the maximum of this curve, and if we don't, we can always find it using implicit differentiation. For example, this is x is equal to 1, this is x is equal to minus 1, this is equal to y is equal to 1, and this is y is equal to minus 1, right? So we know the upper and lower bounds. So if I ask you, what is the area of this region, then you should know, well, the area of a circle is just pi r squared, and the radius in this case is equal to 1. So therefore, this is just going to be equal to pi, or approximately 3.14159, and so on. So if I ask you to pick a bunch of points in this region, what is the probability that the point within this square lies inside this circle? Right? So the area of the square is going to be equal to what? So if this distance is 1 and this distance is 1, then the entire length is going to be equal to 2, and same thing goes for the height. So the area of the square is just going to be equal to 2 times 2, which in this case is going to be equal to 4. So therefore, the percentage of points inside the square that are in the circle is going to be equal to pi divided by 4. So this is pretty much the probability that our point, x comma y, belongs to our circle. That's going to be pi divided by 4. So if I want to approximate pi with a probability method, therefore, and let's assume that this percentage of points that we get that lies in the circle is, say, p hat, because it's not going to be exactly equal to what we want, then we're going to have that p hat will be an approximation for pi over 4, implying that pi can be approximated by 4 times p hat. Right? So this gives us a probability approximation for pi, which in some sense is kind of neat. Right? And I'll do an implementation of this in our studio in just a moment. But obviously, this is not the goal of what we aim to do today. Our goal is to approximate integrals in higher domains. So the natural question is, can we use this same idea for multiple integration? And the answer is, take a guess, of course, yes. And this method is sometimes referred to as Monte Carlo integration. And a lot of numerical methods for higher dimensional integrals will use Monte Carlo integration to approximate. So there will be a sense of randomness to the accuracy and also the error, but there are some numerical analysis theorems out there that give you bounds and give you some thresholds on how to control it. So if we consider our parabolic domain from before, so for example, y is equal to x squared, and let's assume x ranges from 0 to 4, then our domain of focus is going to be this parabolic region here. So if we want to bound this in some rectangular domain, then we pretty much need to consider this point here, which is going to be 4 squared, which is going to be 16. So what we're going to do is we're going to pick random points inside of this rectangle to approximate the area of that rid region, to approximate the area of our domain. All right, so let's actually write that down. So what we do is we can approximate this area. Let's assume that this area is A, like we did with pi. Right? The only difference is the shape. Right? So what we're going to do is we're going to choose points, for example, uniformly in the Cartesian product of 0, 4, so that's x. Cartesian product was 0 to 16, which is our y range. So that's our green square that we have here. And then once we choose points uniformly in this thing, then we're going to check if our point xy belongs to our domain D. If it does, then we use it, and if it doesn't, we don't. Right? So how do we check and see if our point belongs to D? So if we choose a random number x and a random number y, either y is going to be less than or equal to x squared, or y is going to be greater than or equal to x squared, or y is going to be exactly equal to x squared if it lies on that boundary. Right? So if y is less than or equal to x squared, this means xy belongs to our domain, and if y is greater than x squared, then this means that xy does not belong to our domain. So that means we can use xy as a tag point to project for our heights. And if it doesn't belong to our D, don't consider it. So once we have our tag points, and keep in mind, repetition could occur here. It could occur here. But is that really going to be a concern? Right? So if we consider this from some perspective, and let's assume this is the xy axis, and let's assume that this is the fxy axis. So notice that if our region is, let's say, over here. Let's assume this is D and this is not D, so the complement, right? So notice that we're going to be picking a bunch of points in this entire region. So for example, we're going to pick this point, this point, this point, this point, this point, this point, this point. Those are not going to be in terms of our solution, right? Now, if we pick this point, that belongs to our D, therefore we're going to be using it. Notice if we pick this point here, we're going to be using it. Now, if we choose 5 points, it's possible that 4 of those points are located here and the 5th point is located here. If this entire height is roughly flat, it's not going to matter. So let's draw a case where this actually does create a dramatically different solution. For example, this, right? This is a dramatically different region because notice that it pretty much says that the height of this curve is much over there, right? So if we take the average of these points, then the average height probably is going to map somewhere there. So pretty much what this says is if I choose these points at random, then I should be having the same exact chance of choosing a bunch of points up there at random. So these all points should balance out to the same exact height average value as if all of these points were uniformly distributed inside of that domain D. So this is a probability and statistics perspective that on average, if you choose a number of tag points capital N and n goes to infinity, then on average the true height should converge from this particular sequence of averages, right? So what we're going to do is going to find the average of heights of this f of x hat k, where k ranges are 1, 2, all the way down to n, where n ideally is going to go to infinity. And therefore, our double integral all over d of fxy dx dy, which keep in mind is just some volume, is going to be approximated by the average height, which I'm going to represent by f hat. And that's obviously going to be a height, and that's going to be multiplied by our area approximation, which we pretty much mimicked from how we approximate the area of pi. Right? So that gives us an approximation of our double integral, and the process pretty much stays the same for higher dimensions. So let's go to RStudio and see if we can both implement the approximation of pi via Monte Carlo simulations and also how to approximate integrals via Monte Carlo integration as well. So keep in mind, we're going to be coding in R and RStudio for this implementation. If you want to code it in Python or MATLAB, pretty much the algorithm is going to stay the same, just the functions are going to slightly change a bit. So it shouldn't matter that much. And plus, you should be able to take any coding language from one language and be able to translate it into another coding language, especially by this stage in your exploration. If not, then I highly recommend being able to have that skill. It's definitely useful. So what I want to do is start off by defining how many points we're going to have. Keep in mind, the more the better. Let's do 100,000, right? It's definitely something that you wouldn't want to do by hand. Since Monte Carlo simulations are going to be probability-based methods, every time you run this code, it's going to give it a different answer. So setting a seed for reproducibility is obviously going to be useful. For example, we can use a seed of 1, 2, 3, 4 to make sure that you get the same answers as me if you want. Now, let's assume that we want to implement, for example, an approximation for pi, right? Keep in mind, our circle was inscribed inside of a square with side length 2, going from -1 to 1 and -1 to 1 for the height. So what I want to do is I want to choose a bunch of points from -1 to 1 for x. So I'm going to uniformly choose points. How many points? N of them. And I'm going to choose them from -1 to 1. And then I'm going to choose the same for y. So my y points is a random set of uniform points, n of them, from -1 to 1. Keep in mind, notice that this is going to give us 2 n points. But once we take the Cartesian product of them, it's going to give us n points or n pairs of points, right? So n is still 100,000 here. So our percentage of points that lie within this circle are going to be equal to what? So this is going to be equal to the sum, or the number of points that's satisfied divided by how many points, or in R you could just do the mean of the points that satisfy this particular conditional. So it's my x squared plus my y squared. How many points are less than or equal to 1? That's going to be your percentage. And then your pi approximation, keep in mind, as we derived before, is going to be that percentage multiplied by 4. So if we take a look at what this approximation gives, it gives us 3.13432. Now, is it exactly equal to pi? No, of course not. You know, some seeds will give different approximations. For example, if I choose the seed 5436 and then rerun these values, it's going to give us 3.142. Notice that for the previous seed, you know, it was 2 decimals, wasn't accurate, but this one gives us 2 decimal places accurate. It's a probability method, but keep in mind, the larger this value of n, the more closer it should become. Now let's see if we can go ahead and use this Monte Carlo approach to approximate integrals, right? So MC approximations for integrals, right? So let's assume that we want to approximate the integral from 0 to 4 and the integral from 0 to x squared of sine of x squared plus y squared dy dx. So this is the example that I mentioned before. And again, let's assume that we want 100,000 rectangles, and then let's set a seed of 1, 2, 3, 4, or whatever seed that makes you happy. So what I want to do is just choose from a random box. For example, my x, remember, we're going to choose uniformly. And some people will do normal, but I don't recommend that because changing this definitely will depend on the domain you're working with. Uniform is always a safe bet. So we're going to choose from 0 to 4. This is obviously for the x domain. And then what are we going to do for y? We're going to randomly uniform from 0 squared to 4 squared, which in this case is going to be equal to 16. So this is going to be for our y domain, in particular our bounding box form of it. Right? So once we have that, that's going to give us our x domain and our y domain tag partitions. And obviously the bigger area, let's call it big area, is going to be equal to 4, that's the length, and 16 our height. That's going to give us our larger area. In this case, that's going to be 64. We're going to need that a little bit later on. So once we have that, then we're going to look at all of our tags that satisfy our constraint. So our tag is going to be y is less than or equal to x squared. So my y's need to be less than or equal to my x values squared, and this is obviously going to be either true or false. Right? So if we look at, for example, my tag, this should either be a bunch of zeros or ones. So if we look at it, it's a bunch of trues or falses. Trues are by defaulted 1, and false is going to be defaulted to be equal to 0. So all points that are true we're going to use, all points that are false we're not going to use. Right? So once we have the points in our tag that we're going to use, let's create our function. So let's call it my function, and this is going to be a function of two variables, x and y. So what is this function? It's going to be sine of x squared plus y squared, and this will allow you to easily adapt this function to whatever function you want to do. And then our function evaluated at each of our tag points is going to be equal to my function evaluated at my x, which ones? The ones that satisfy my tag values, and then my y values, which ones? The ones that are inside of my tag values. So that's going to be the heights of all of our points that satisfy our constraints. Once we have our heights calculated, we also have our base length calculated as well, then we can approximate our integral estimate. So I'll call it int estimate, and this is going to be equal to what? So this is going to be equal to the average of all of our function values that satisfied our tag points, and then we're going to multiply that by the mean of my y less than or equal to my x squared. So that's going to be approximating our base length, and then that's going to be multiplied by our big area in order to normalize everything back into the correct units. So once we have that, that's going to give us, a big area shouldn't have an underscore, that's going to give us an approximate for our integral. So if we take a look at what this integral is, it's approximately equal to 0.35. Let me take a moment and see what the exact value of this integral is just for comparison. Using some more advanced integral methods in particular, for example, the things that are pre-built, say in MATLAB, sometimes Desmos approximations are pretty solid as well, or Wolfram Alpha, you're going to get an exact area of 0.3405, right? So true should be 0.03. True value of 0.34. 0491-ish, right? So the difference between these are actually really, really good, right? Even though we're only using 100,000 points. Right? So you definitely see how Monte Carlo simulations are definitely appealing because the implementation of these integral calculations is actually very, very short, and you don't have to do a lot of pre-processing for the domain that you're working with. But there are other, of course, numerical methods for higher order dimensional integral approximations that we may return later and explore. But I hope you enjoyed this video on integral approximations, and I'll see you in the next multivariable calculus video. Take care.